Okay, so I had a couple of requests for students to do the hang time question from the test, and so I'm going to make this video and then I will be uploading it later today. So the idea is this, that when a person jumps into the air, they seem like they hang in the air for a long time, or at least they hang, up in the top part of the jump for like a longer amount of time than you would think, because it's going to go whoosh. That's what it seems like. So the question is, when somebody jumps up, what percentage of their time do they spend in the top 10% of their height? That's the point of the question. So the instructions for solving the question are actually right in the question. This percentage is totally independent of how fast you jump. So you could have, it's whether a person jumps high or jumps quickly or jumps slowly. You will always spend the same amount of time in the top 10% of your height. So the instructions say to just pick an initial velocity up, and it's best to just pick a nice round number. I'm going to pick 2. So let's say a person jumps with an initial velocity of 2 meters per second. We want to figure out what is their max height, how long does it take to get there, and then what is their 90% of that height, and how long does it take to get there? Because if we know how much time it takes to get to the top, and then how much time it takes to get to just 90%, that means we're able to figure out how much time is spent in the top 10%. The key for this problem is that your jump or your motion is symmetrical, so the same amount of time is spent on the way up as spent on the way down. That's from a note on one of the PowerPoints. So we really only have to analyze the time spent on the way up. Because let's this argument say that you spend 20% of your time up here. Well, that means on the way back down, you're still going to spend 20% of your time at the top 10%. So it's easy to solve it this way. Okay, first things, how high do you go? Well, VF squared equals VI squared plus 2AD. We're trying to figure out how high you go. The final velocity at the top of the jump is 0. So VF squared minus VI squared all over 2A is going to equal this max height. So it's going to be 0 squared minus 2 squared all over 2 times negative 9.8. So this will be, and it's negative because my reference frame is positive up. Gravity, of course, would be downward. So we have negative 4 divided by negative 19.6. So 0.2041. So he goes, so 4 divided by, okay, 0.0241 meters. And I'm not going to round very much because this is a small number, so I definitely don't want to just shave it to 0.2 because you end up losing some of the point stuff. So again, this is the max height. So 0.2041 meters. Okay. Now how long does it take to get this high? Well, we're looking for time, so there's a couple ways you could do it. Probably the easiest way is to do VF equals VI plus AT. You could use a distance formula, and you'll get the same answer either way. At the top of the jump, the final velocity is 0. At the initial part, it was 2 minus 9.8 times t. And so if you want to figure out how long it takes to get to the top of your jump, it's going to be 2 divided by 9.8. So t is 0.2041 seconds. And I just want to point out that it just so happens that these are the same number. It's not always that way. It's just with the number 2 here. Long story short is because there's a factor 2 here. Again, it's just total coincidence that the distance and the time are the same, so don't read into that. Any other number and it would not be the same. Okay, so it takes that amount of time to get to the top. Okay, so what's 90% of that height? So 0.2041 times 0.9 is, so 90% of the height is 0.1837 meters. Okay, this is an important number. Now the question is, how long does it take to get to this height? Well, we can't use this formula to get this particular time anymore because we don't know what the final velocity is at the top right here. It's definitely not 0 because it's 0 up here. So we don't know what VF is, so we can't use this formula. We're going to have to use the distance formula for here. But we can set our final distance as this distance. We're starting from the ground. We have an initial velocity of 2. and then minus 1/2, or you could say plus, and put the negative sign in here if you want to be super technical. Maybe I'll just do it that way so it follows your notes a little better. And now you can see that this is going to be quadratic. So 0.18, sorry, it's going to look at negative 4.9 t squared plus 2t minus 0.1837 equals 0. Here's your A term. Here's your B term. Here's your C term. Okay. Now my quad solver is being used by the iPad to record this, so I'm going to work backwards just a tiny second right here. So 0.2041 times. Let's just call this T. This will get you, by the way, this will get you two roots. One root will be positive, one root will be negative. You can't have a negative time, so you want the positive root. So we'll just call this T90 for the time to 90%. And again, your quad solver will tell you the time. It's certainly less than this time. And in fact, I already know what that time. Let me just quickly crank it out. So let's go. So this time is actually going to be 0.1396 seconds. Okay. So when you do the quad, you'll get this as one of your times. So now I'm just going to erase a little bit for a moment. And now let's think about it. It takes you 0.2041 seconds to get to the full height. And it takes you 0.1396 seconds to get to this 90% height. So how much of your total time is spent right up in here in this top 10%? Well, that's the difference in time between this and this. So let's just crank that out real quick. So this amount of time is 0.0645 seconds. So that's how much time. So what percentage of your total time is this time? Well, that's just going to be this divided by this. And you get 0.316, which is 31.6%. So the answer to this question is you spend 31.6% of your total flight time in the top 10% of your height, which means you spend a third of your time at the very, very top of the flight, top of your jump. That's why it seems like volleyball players, basketball players, long jumpers, anything where you're jumping, they seem to have this hang time. They seem to almost like float a little bit. Like, again, you spend a third of your time at the top 10% of your height. So this would have been the answer for the flight time question. And again, if you followed the instructions on the question, hopefully you got that answer.